fact that double negation need not be the identity, it can be something larger. So this may seem a little exotic first, but it's a very natural thing. And the prototype example for Heyting algebra are the open sets in some topological space. And I think it's nice, and I want to show this in a minute. The question, of course, is what to do, how to define the lattice operations in an open set. So I can take the intersection of open sets and get an open set. I can take the union and still get an open set. But what about negation or complement? If I take a complement of an open set, I get a closed set. Well, this is not what I want to do. I would rather like to take the interior of the complement, and then I'm back to open sets. But if I do that, and then, for example, look at the open disk around the origin, but with the origin left out, this is an open set, of course. Taking the complement is, well, it's all outside here, and the origin, but the interior of that, the origin disappears, and it's all the outside. Then taking the complement of that again gives the closed disk. The interior of that is the closed, is the open disk, but with the origin. So double negation gives us the open disk with the origin, which is larger than the set we started from. It's a very simple example for this relation down there. So,
can I? Yeah. For computer science, this has to do with finiteness, because like the open is where you can get infinite time, while the border you need infinite time. You need the limit. So for them, it's a very sort of again natural situation to have a Heyting algebra. It's what you can reach in finite time, computability theory and stuff like that.
oh yeah.
So that's where they use topos for that, to implement that idea that in finite time I can reach this.
Mm-hmm.
It's a nice way of presenting it.
Yeah. Okay.
Yes, and we'd also dovetail with the fact that, for instance, Kripke semantics also live very naturally inside the topos, which is a very similar motivation.
For similar reasons.
As time,
Yeah, well, this type of logic, and this is why I said we want to use a very special case here in this presentation. This type of logic is typical for topology, so this is nothing special to this topos appreciates. Of course, there are topology like set itself, which are called Boolean topology, where we do have a yes-no logic, but in general they have this intuitionistic type of logic. And what we did before was sending projections seen as propositions about a quantum system to subobjects of sigma. And now we see the subobjects of sigma are a Heyting algebra. And this is what we suggest. We want to talk about quantum propositions in a new type of logic given by the topos. This, of course, is a non-distributive lattice. Well, this is a distributive one, so this cannot simply be a lattice morphism. Something must be different. In fact, we can show that the OR is preserved, but the AND goes wrong. But maybe this is not right to say it goes wrong, because we saw that the logic here is nothing we can really work with. Well, this is much closer to what we're used to, and it's really internally in the topos. It's nothing that we imported or put on these things, but it was simply given as a part of the structure of the topos. And it's a fact that there are more elements in this Heyting algebra than those coming from projections. So this is a richer logical structure. And we still have to interpret this a lot. Of course, there's a lot of work to do, but what we can say now is a rich structure, and it's simply a new way of talking about quantum logic. We could call this topos quantum logic, big word, but you see what it means. We map quantum propositions to a distributive lattice given by the internal logic of a topos. So what about states? This is very preliminary. This is surely not the final form of these. Yeah.
What is, perhaps I missed it, what was the sub-object classifier?
A subobject classifier is a little hard to explain. In this category, I didn't say it explicitly. This is
it's complicated.
no, it's the pre-sheaf of sieves, and sieves are the following stuff. If you have your category, and this is, as I said, a very simple category on the opposed set. Then sieve on V is a collection of subalgebras of V prime contained in V. Well, maybe I shouldn't make this more abstract. I should say more abstract. Sieve on some. It's a collection of so I collect morphisms that all land at A, so to say, such that whenever when we have some other morphism, or we have some f going from, let's say, B to A is in this sieve, which I call S, f is in there, and we have some other morphism going from C to B, then the composition well, I must take f of G going from C to A. So it's downward closed in some sense. It takes some, you have some morphisms landing at A, and whenever you have some other morphism landing where this point starts, then the composition also landing at A must be this, so it's downward closed in that sense. Okay, this is the, and then these sieves on the distributed subalgebras, they form a pre-sheaf also, and this is the subobject classifier. In this special pre-sheaf, in this topos we are looking at now. More generally, the subobject classifier is defined by this diagram that I showed, and it's, of course, it's an abstract definition because it's a very general notion. It generalizes the set of truth values, but you should not think of it as a set necessarily.
I was thinking it had some sort of physical.
Oh, we hope it has. We try to show it has. Okay. Well, this is, what about states? As I said, this is very preliminary. This is what we're trying to do currently, and I'll say a little more on this at the end of the talk, is to rewrite everything we have in quantum theory internally in the topos. So we want to see if we can do that, and so we will have to say something about states and what would we expect the state to be. If we go back to what we usually have to do, classical physics, and there we would have the topos set, the pure state, such a pointed phase space. This can also be seen as a morphism from the subsets of phase space P to this 0, 1, which is the subobject classifier. So it's a little more than morphism, a lattice morphism in fact. Yeah. This may seem very abstract, but in fact it's really not. It simply says that if you have these subsets of phase space, they correspond